So last time we started multilinear models, right? So this will obviously compute a multilinear polynomial, but the condition is that every gate in the circuit should be computing a multilinear polynomial. So sometimes this is also called a syntactically multilinear circuit. So to study these models, the measure that we will look at is partition the variables x into y disjoint union z, and then draw a matrix where you have rows y monomials, columns z monomials, and an entry will be the coefficient, corresponding coefficient in the polynomial. So this, by the way, doesn't need any circuit model. So this is really a definition for multilinear polynomials or even general polynomials. You can take any polynomial f and you can draw this matrix. And then you look at the rank. So that rank is the measure gamma. So this is the measure gamma with respect to a partition of f. So what we have shown is for two polynomials, measure is upper bounded by the sum of the measures, respective measures. So that is subadditivity. We have shown that for two multilinear polynomials on disjoint variables, there is exact multiplicativity property. So the measure of the product is product of the respective measures.
We have used multilinearity of the final polynomial, but we have not used multilinearity at every gate or something.
No, these are not circuits. These are just polynomials. Till now, circuit has not been used. So there is subadditivity, there is exact multiplicativity property, and we showed that if we multiply f by a polynomial that is either y free or z free, then the measure doesn't change. Yeah, this also did not need multilinearity. Yeah, this is just it is true for any polynomials. And finally, we showed that the measure never exceeds 2 raised to min of y, which is really the number of rows, or 2 raised to min of z, which is 2 raised to z, which is the number of columns. So rows and columns, minimum of that gives you the upper bound on the rank. And this is tight, as we saw in this example. In this product, you can see that the number of y monomials is 2 raised to n, and so is the z monomials, and the rank is also that. So this is a depth 2 example, right? This is pi sigma example. If you think in terms of circuits, then the circuit here is just product of sum, and sum is just doing adding two things, two variables. Right, so what we now want to do is we want to show that although there is this pi sigma example with measure as high as 2 raised to n, so maximum possible, still there is a way to, there is a way to reduce this. Okay, there is a trick by which we'll use this measure on pi sigma circuits and show that the measure is small in some sense. So once we have shown this, then the opposite of this will be that we take determinant and show that the similar trick gives a high measure. Okay, so what is the trick? So the trick is that you do not partition in this way. So here the partition that we chose was actually worst possible, So it gave you the maximum possible value of the measure. What if you change the partition, right? So don't follow these yi's, zi's partition, but let us say randomly pick a partition. So if you do that, then you will see that the measure actually falls. Okay, that is what will make this useful for proving lower bounds. So Raz showed that the measure for pi sigma circuits can be significantly reduced if we consider a random partition of the variable set. Okay, so remember that this matrix that we draw depends on how we partition the variables. There are exponentially many ways to partition the variables. So even if there is a single partition that reduces the measure, it can be good. So in fact, we will show that most of the partitions will be of this type. The measure will be quite small. It will not be sub-exponentially small, but it will be much smaller than 2 raised to n. So that's the theorem, upper bound. So consider pi sigma polynomial or circuit. So it is a product of linear polynomials d many on n variables. And importantly, they should have disjoint support, right? So that f is multilinear. So let f be an n variate multilinear polynomial. So for a random partition, and let's say these are equal parts, we have with high probability so the measure will be smaller than 2 raised to n by 2 by n by 32. Okay, so the exponent falls just by a constant multiple. It is not a big fall, right? But since it is happening in the exponent, I mean overall it can be useful because you just have to now show that for some other polynomial like determinant, the measure is greater than this, right? So now you have some gap that you can utilize. With 2 raised to n by 2, you had no gap. So now, so this creates a gap that we can try to exploit later. Is the statement clear? Yeah, so once we have shown for product pi sigma, for sigma pi sigma also we have this similar upper bound because by subadditivity, right? So this upper bound is really for multilinear depth 3 circuits, right? So this measure is that powerful. It can actually analyze properties of multilinear depth 3. Okay, so the way we will prove this is it will be an easy proof. We'll essentially show that if you randomly pick y, this part y, then many of the LIs will either be y free or z free. if L1 is Y free, then we know that it will not contribute anything to the rank, to the measure, right? So if we can show that a large number of LIs drop out of the race, right, that will give you the difference of n by 32. So that can be shown probabilistically. So let us assume first of all that each Li has greater than equal to 2 variables. In the support. If not, then they anyways don't play a role, right? So we don't consider univariate LIs. So LIs are at least bivariate or more, that we can assume. So now this implies that the measure for F is bounded by, yeah, this anyways, I mean, this was always true. The just because F is a product of D many
Each of them is ranked like greater than equal to 2.
L1.
Each of them, because we have taken greater than equal to 2 variables in the support. Why should they not?
No, the rank of L1 is at most 2. It's a linear polynomial. So rank of each Li is at most 2. So just product is 2 raised to D. This does not need any assumption. This is true anyways. In fact, I should say just we have this always. Since and then multiplicativity. So what this means is if D is too small, right, if it is smaller than this n by 2 minus n by 32, then anyways we are done. So we are done if in particular D is less than n by 3, right, because then you get an upper bound of 2 raised to n by 3, which is even smaller than what you wanted to show. So we'll assume that D is bigger than n by 3, or at least n by 3, and each Li has at least 2 variables, and Li's have disjoint variables, right. So this gives you a constraint system. So since Li's are disjoint support, and many, so we get by an averaging argument that number of Li's with support size two or 3, so basically smaller than 4, right. So number of Li's with support size less than 4 is at least D by 4, right. Why is that? Right. So else you will get that greater than 3D by 4. So if it is less than 3D by 4, then more than 3D by 4 many Li's have support size 4 or more. Which would imply that the number of variables is greater than 3D by 4 times 4, which is 3D. right? But we have assumed that D is at least n by 3. So that's a contradiction.
That's symbol for contradiction.
Yes, the lightning strikes. Yeah, so since LIs are many and they are disjoint, they cannot each have many variables, right? So in other words, many of the LIs have minimum support possible, which is 2. So we get for 2 and 3, we get this quantitative estimate of D by 4. So we call these LIs small. And we'll only care about them in our probabilistic argument. We know that these are present, so you can assume that the initial D by 4 have support less than 4. They only have 2 or 3 variables. Li, we have so what is the probability that when you randomly choose y of size so y has n by 2 variables, so that fixes z also, then this particular Li is either both all the 3 variables or all the 2 variables are in y, they fall in y, or they fall in z. So whatever is the probability, it's a constant.
N by 2 choose 3 by n choose 3.
No. There is no. We won't do that calculation. So every so variable x1 will fall in y or z with equal probability.
Right, but then they won't be independent. Variable x1 and x2 won't be independent because you have the additional constraint that y has size n by 2. So it's not the case that for each variable you're independently picking whether it falls in y or z. Because then only the expected size of x, y and z will be n by 2. Here you have that additional constraint. So you're not independently at random for each variable. Amongst all subsets of size n by 2, you pick one at random. The distribution will be slightly different.
No, but I want to write here. So all the 3 variables falling in y.
So that will just be n by 2 choose 3.
Right, so I have to write that expression then. So maybe I give the exact expression. So it will be what? For falling in y, all 3 is so here the number of ways of choosing y is n choose n by 2, and if 3 fall in y, then n minus 3, is it? But I don't like this.
No, that expression is better. N by 2 choose 3 divided by n choose 3.
N by 2 choose 3
divided by n choose 3. No, that's not correct.
N by n choose 3.
You need something like that.
No, this seems to be the only expression. x1, x2, x3 you have put in y, and then what remains is just n by 2 minus 3. But is this?
No. So that expression works because the total number of triples that y contains.
No, but the argument has to come from this. So what is this?
But this argument too, right? The total number of triples that y contains.
No, but I don't want to erase this. No, I don't want to erase this now.
Forget this.
No, this is the simplest expression. So this is n minus 1, n minus 2, and and then we get n by 2, n by 2 minus 1, n by 2 minus 2.
Yes, same thing. And that is 3 by
So, so this we can see is it more than 1 by 8? Should be.
Yeah, because
Yes, it has
each term is slightly smaller than half.
Slightly smaller than half, yeah. So, yeah, so let me then not venture into its exact calculation, just say that this is very close to 1 by 4.
But this is questionable, right? Because it actually depends on n. The probability will depend on n.
Right, so n is asymptotically growing. So, as n tends to infinity, this is just 1 by 4, and so which is okay. I mean, we just wanted some constant probability that we have got, and so this means well, I'll kind of need this 1/4 for the subsequent calculation. So let me continue with this 1/4. So this gives me the expectation of so when you pick y randomly, then y is either completely in y or completely in z. That probability comes out to be around 1/4, and so number of i's amongst these small li's. So we have shown that probability of Li being y free or z free for a fixed Li and small is at least 1 by 4. That gives us the expectation of 1 by 4, which is the probability, times d by 4, which is the number of small Li's that we have seen before, this number. So the expectation of these small Li's that ultimately will not contribute to the rank or the measure. Right, this is this number of these i's is expected to be d by 16. So these Li's stop contributing to gamma yzf. Right, so essentially out of d, 1 by 16th are not contributing. So that gives us the gap in the rank. So this implies that gamma f is at most 2 raised to d minus d by 16. Yeah, for now I have to use a fancier notation. Then this 2 raised to d by minus d by 16 is at most so d is at most n by 2. Right, this is because we have assumed every Li has at least 2 variables and they are disjoint variables, and d is at least n by 3, so that gives us, so that will give us so let's write down the properties of d. So d is less than or equal to n by 2 and it is at least n by 3. So what do we get? We get n by 2 here and we get n by 48. Yeah, that is what we should get. So we have to change the theorem statement accordingly, but then we get this gap of n by 48. Is that clear? And right, so we can write a corollary here that for multilinear depth 3 circuit F with S product gates. So let us just use sigma pi sigma, where the top fan in is S. So for this with high probability, the measure is at most S times this. Right. So multilinear depth 3 and N variate. Which has S many product gates, then you get by subadditivity S times 2 raised to N by 2 minus something. So that's the upper bound, and now if you pick your F suitably, which will be determinant, and show that the measure is large, so that will give you S bigger than some bound, which will actually be, we will show it to be exponential. Right, so let us now go to the other part, which is why does determinant have a large measure. So determinant and permanent n cross n matrix have high gamma. So det n has n square variables. Yeah, so any ideas how to show that the measure is large? So again, if you are not careful with the partition, right, so n square variables, yeah, if you are not careful, then the measure can be really small.
Only a small number of
How will the function matter? It's symmetric.
the size.
Symmet-
Size.
It's the size.
You know why exactly are different sizes?
What do you mean symmetric? The partition is not symmetric. You are picking a subset of the variables. Yeah, so I mean you can come up with small examples where when you pick different partitions, the measure will change widely. So we'll not go into those nitty-gritties. We'll just continue with our probabilistic argument. That probabilistically, if you choose y, then the measure will be high. I don't think it will be an optimal result. So what we'll actually do is we will set a large number of the variables to 0, and in the remaining variables we'll call the remaining variables x, and that is where we'll do the partitioning. So we will reduce the variables by fixing them mainly to 0. So let me not say where we are fixing. So we'll reduce the number of variables to a random x, to a random variable set x, which will be much smaller. So now this x will be of size 2m, which is around square root n. Okay, so size of we'll basically set a large number of variables to be 0, and we'll be left with around square root n variables out of n square. Right, it's a big fall. and then use a random partition. So this does not look optimal because we have killed many variables. Ideally, we should have reduced to somewhat n many variables. But for the proof to work, we'll go to square root n. It probably is related to the Berde paradox. So the probabilistic calculations will need square root n. So that's the definition of x, m, and y, z. Okay, that's how we'll do it, and then we'll show that the measure gamma with respect to this of evaluated determinant or restricted determinant is high. Yeah, so determinant we started with n square variables, we reduced them to n to m or 2m, and if determinant had a depth 3 circuit, then there also the variables will reduce to 2m, right. So in the previous lemma we are getting something like a gap of m by 48 or whatever, m by 24 and that is what we are up against. So we have to show that determinant has measure just more than that to get a lower bound on S. So we will prove this theorem, which will be enough. So this is due to Raz, same paper. So with probability at least 50%, a random restriction sigma of the variables n square variables 2x x of size around 2 square root n by 5 yields a large measure not determinant but this restricted by sigma. Okay, so this measure will be exactly 2 raised to m. So remember that there are 2m variables. So this is like in the exponent you are getting half of that, and so when you compare this with the previous theorem, the difference which you got, that is basically giving you a lower bound on S. So it's exponential, but since m is square root n, you get that S is at least 2 raised to square root n, right. So it's not, it doesn't seem optimal, but still it is kind of exponential. It's an exponential lower bound to compute n cross n determinant. Okay, is the statement clear? And the connection between the lower bound and the upper bound theorems. So the way we will prove this is, yeah, the thing which we always do with determinant, that to give a lower bound on the rank, we somehow identify triangular or diagonal structures, right, and using that we show a rank lower bound. So that will be done by essentially by sigma. Sigma will fix the variables in such a way that you see a diagonal structure, diagonal block structure, which is easy to rank bound. So the map sigma will fix n square minus 2m variables to f values in a certain way. The remaining variables we are calling them x. So let us compute the probability that these remaining variables, they do not share a row or a column. Okay, so if you have a variables v1 and v2 in x, then we want v1 v2 to be in different rows and in different columns. Right, this is again, the intuition is to get somewhat diagonal block structure. So let's compute the probability that these variables x don't share a row or column. Right, so this is kind of a two-dimensional version of Birdie paradox. Sorry?
Collecting it, right? Where you want to collect all this thing, stickers or whatever. Because once you pick one, then the probability of the next one reduces a little bit, not by n minus one.
You put variables compare.
Right.
And every time you put a variable, that one,
Yeah, that row is
Yeah, so it's that. So sigma is a random evaluation of that many variables, and you want x, the remaining variables, unfixed variables x, they have different rows and columns. So this probability exactly is well, first, so okay, we are looking at this process as if picking the variables of x. Okay, not fixing variables, but just picking these free variables. So the first free variable is free. You have n square favorable choices, but once you have picked it, then you have picked a row and a column, so they are gone. So now you are left with n minus 1 square possibilities, and this then n minus 2 square and so on, and you want to pick no, so in terms of m, so n minus 2m plus 1 square, so that will give you the 2mth variable. All possibilities are n square. So this is this is the same expression you get in Birdie paradox squared, right? And so you have this intuition that m should be less than or yeah, it should be on the lesser side of square root n. If it is on the larger side of square root n, then this will be a problem. So that is why we needed m to be square root n by 5. So this is greater than 1 minus well, this will need a slight calculation which I am skipping, but the intuition is that 1 and then you have a negative term, then you have a positive term and so on.
Show this very easily inductive. I think the product one.
Yeah, so do that as an exercise. That's the question mark. And so the larger contribution comes from the first two terms, and the remaining will only increase it. Okay, so it's this sigma I by n that you have to estimate then, which is for which you know the lower bound, so that gives you an upper bound. For which you know upper bound, so this will give you a lower bound. 1 minus right. So for the square we take the 2 inside, and then sigma I is what we have estimated. Okay, and this comes out to be more than 1 minus 4 over 25. So this is a huge probability, right? With a very large probability, x will have different rows and columns, variables in x. So what is the advantage of that? So these are the free variables, and the remaining are all fixed to constants. So how does your determinant matrix look like? So for such a sigma, the determinant n shares its properties with the following structure. So this is only 2m cross 2m. Yeah, so this will need some explanation, but I will not go into all the details. So you started with the n cross n matrix, right? You fixed a lot of variables, leaving only 2m variables free, right? So assuming that these variables, remaining variables or free variables, are organized in a diagonal fashion, right? This 2m cross 2m matrix is the matrix which will give you, which is the kind of the symbolic part. Everything else in the original n cross n matrix is fixed to constant, and they are fixed in a random way.
Why do zeros over here?
Yeah, so that is because I just want to say that it shares its properties. It's not exactly this. So the zeros are also random values in general for a general sigma. But look at this matrix. So this matrix has determinant. So its determinant is equal to product of yi zi minus 1. Right. So if you get to this matrix, then its determinant is something which we understand, and that is product of yi zi minus 1. So let's call it dm. So this is really the variable part, and for this random sigma, what you will get is this multiplied by some constant and plus another constant. So when you will look at the measure, you are really computing the measure of this polynomial, this 2m variate polynomial. Is that clear? Yeah, so to work out the details, you have to assume that sigma was fixing the other variables to random points. That will be needed. So in general, you will have, thing that I have skipped is this is a bigger matrix, where here you have constants and here also you have constants, and these are also constants and not 0. But when you will start differentiating this, the measure that you will get that measure will be lower bounded by the measure of dm. That is the thing to realize. Okay, so from now on we will just discuss gamma of dm. Okay, this is the n cross n, and we have identified a submatrix and the determinant of that, and let us look at the measure. So this really is the reason, this picture is the reason why we are doing all this fixing of variables and keeping 2m variables free in the end. So any question about the overall idea? The details I leave. This picture should be worth 1000 words. Okay, so now so this may be the exercise, that with high probability for a random sigma gamma yz of sigma determinant would come out to be gamma of dm. And what is this high probability? So this, how much is the error here? I think if you assume the field to be larger than n in size.
The theorem, right?
Sorry?
Even that probability which you claimed in the theorem. This high probability.
No, for this event, that gamma sigma determinant is gamma dm. The probability of this happening is given by the Schwarz-Zippel lemma. So basically n over the field size is the error. So if you assume field size to be bigger than n, then 2n, then you get probability half or probability 1/3. So we can assume here that error probability is less than equal to 1/3 by Schwarz-Zippel kind of argument. Yeah, so whatever I have said, this will happen by the random fixing with probability at least 2/3. Okay, so at least 2/3 probability, we can reduce the study of gamma of sigma of determinant to gamma of dm. And then gamma of dm is something that we can calculate. So what is gamma of dm? It is like yi plus zi calculation that we did. So it is 2 raised to m. Remember that y is the set of yi's and z is the set of zi's. So for this polynomial, the partition is the worst possible. It maximizes the measure. So you get 2 raised to m. So that's the lower bound for determinant, measure lower bound for the determinant. So last thing is we have to be sure about the probability, that the error probability is not too large. So let's check that. Probability over sigma that gamma yz sigma determinant equals the measure for dm. Which is 2 raised to m. Maybe to be sure, I should put an inequality here. I think I only care about this. I don't want them to be exactly equal. So probability that the measure of determinant after restriction is at least 2 raised to m. so that picture holds, right? So that depends on two things. One is that choice of x variable should be in this diagonal fashion, and second is fixing of the variables to constant should be good. If you do an unfortunate fixing, for example, you set everything to 0, right, then the rank will just fall, DM will not help. So those two errors we have to check. So choice of x carefully is 4/25 error, and fixing of the remaining variables is error 1/3, right? So this is still greater than half. So that is the probability of the lower bound. Okay, so there are at least half of the choices of y give you a large measure, where by large we mean for n square variables we are just getting 2 raised to square root n lower bound. Okay, so this is not really optimal. I would have preferred 2 raised to n, but the probabilistic argument goes via Berde paradox, and so you get slightly worse. Any general questions about the proof? Okay.
So there is some other method by which you can do better. This is more.
You have to study probabilistically, right? This the upper bound was a probabilistic upper bound. So then lower bound also should be probabilistic. Otherwise, how will you match the two? And if you try to do this probabilistically, then you get into Berde paradox. So I am not sure whether this 2 raised to square root n is optimal. Is there an example somewhere? I don't think this is resolved. Right, so now we are set for the we can connect the two. So we deduce an exponential lower bound against multilinear depth 3. So yeah, so we did only for determinant, but you can see that this argument doesn't really care about the difference. So permanent also will, once you have this diagonal block structure, permanent will behave as well. It will give you just yi zi plus 1. So that will not change anything. So this is really trivially the same, directly the same proof. So determinant or permanent require 2 raised to omega square root n size multilinear depth 3. Right, so this is what you will get, but I don't think we know any such constructions. So we don't have a multilinear depth 3 representation for determinant available, neither for determinant nor for permanent, right, over any characteristic field. So for permanent, what you know is multilinear depth 3 of size 2 raised to n, and for determinant I cannot even think below n factorial, which is n to the n. So we don't really have such constructions. This most probably is not optimal, but still it's a strong lower bound. So suppose determinant has such a representation. Suppose determinant is Cx bar for a multilinear sigma s pi sigma circuit. So then apply as before, as described before, a random variable reduction. Sigma both sides, right? So you will get sigma of determinant is sigma of C. So this will bring down the variables from n square to around square root n, 2m. So this becomes 2m variate now. And yeah, then you apply the measure both sides. So on one hand you will see that gamma of determinant in the probabilistic space of choices, this is with high probability 2 raised to m. On the other hand, gamma of sigma of C. So note that sigma of C is still sigma s pi sigma, right? So multilinear depth 3, this is quite important, that multilinear depth 3 structure has not changed by sigma, because sigma is either fixing the variables or it is keeping them free. So this will not change. I mean, this can only reduce the product fanning, it cannot increase it, and it will not change the sigma by sigma structure. So we can apply the upper bound, which with high probability comes out to be s times 2 raised to, so now number of variables is 2m, right? So 2m by 2 minus 2m by 48. So note that this is quite precarious. So the 2 raised to m cancels both sides. So whatever is the minus part, that is the lower bound on s. So this gives you s greater than equal to 2 raised to m by 24. Right, which is yeah, so just 2 raised to omega root n. Is that clear? Did I make a mistake in the representation claim? Yeah, that was wrong. So for determinant, actually by depth 3 reduction, you will get a depth 3 circuit of size n to the root n. Oh, but it will not be multilinear. Yeah, it's not multilinear, but it's yeah, if you look at the size bound, then this 2 raised to square root n is close. So the multilinear structure is what what? No, depth 3, to come to depth 3 you have to use a duality trick. Those things are inherently non-multilinear. Otherwise you will keep on hanging at depth 4. So determinant, it's sigma pi sigma complexity is n to the big O of square root n. So this we know over good fields, assuming the characteristic large or 0, we know that there is a sigma pi sigma representation, but it's not multilinear. So that is open. But still it is interesting that the quantitative bound you are getting is 2 raised to square root n, which is kind of matching with n to the square root n, but qualitative difference is that this multilinear restriction is
n to the omega log n.
sorry
This is n to the log n.
n to the log n. What is log n?
So this S bound. I mean, we have n to the order root n.
Mhm.
Gap, right? The gap.
In the exponent, the gap is of log n.
Log n.
Mhm. Yeah, so this is O tilde square root n. Yeah, so if you can compare O tilde with omega, then it's the same. But we don't have a multilinear representation. So that seems very unlikely, coming to depth 3 with multilinear. So anyways, this is the status. So next thing we should do next time, which is tomorrow. So tomorrow what we will do is we will generalize this to higher depths. To constant depth. Multilinear circuits. Okay, so the point of doing sigma pi sigma first was to give you a baby introduction to the proof technique, and then the real thing will be going to constant depth and then finally going to formulas, multilinear formula. Okay, so we will show that determinant, if you try to express it as constant depth multilinear circuit or like a multilinear formula, then it has to be super polynomially large. Some more combinatorics will be required for that. Basically in the upper bound part. The lower bound part is the same. In the upper bound part we have to show that even these constant depth multilinear models or multilinear formula models, even they are weak in this measure sense.